Hey, okay, welcome here. We're working on our, believe it or not, our last electronics lab. This is the lab for week 9, and as you guys know, starting in chapter 29 last week, you were starting to learn about the second half of this class, and magnetism. That's why it's called electricity and magnetism. And so our next lab we will be on magnetism. But one more good one on our electronics here before we switch over into magnetism, and that's Kirchhoffs Laws. And so on page 27, go ahead and get out your PDF and go to page 27, and you'll see the title. It's Kirchhoffs Laws here. He starts off by saying, let me just remind you of them, and so maybe I will also, and so I'll go ahead and just say, if you had a wire that was coming in, and then we call this a node, and so maybe it branches off, and maybe just to keep it going in some kind of a symbol, maybe I'll say the current comes in from resistor number 1, splits, and goes to resistor 2, and then resistor 3. Maybe even the current groups back together and completes a circuit, maybe something like this. The Kirchhoffs laws are twofold. One of them is based upon conservation of charge. What it says is what's coming in this way. If I call this number 1, when it hits this node and splits off, and maybe I'll call it then number 2 and number 3, that is the current going in. Current number 1 must be equal to the currents coming out. So that's our conservation of charge. Because clearly if it wasn't, something would be going on like this. If it wasn't, maybe charges are just like magically disappearing, and we know that doesn't happen. That's the principle of conservation of charge. Maybe they're being added. Again, that doesn't happen. Maybe they're building up, and so you're getting like a bunch of negatives just stuck here as everything else continues on. But you can't have that certainly in a long term. Maybe you can get a few of them, but kind of like cars down a road, if a few of them pull off, 1 or 2 is not bad, 3 or 4, but they stop other ones from being able to pull off, and so it doesn't continue for very long. So anyways, that is the Kirchhoff's node rule or junction rule, and so that's what he says is rule number 1 here on page 27. And of course the other one is a conservation of energy answer. It is if you add up all the voltages around a loop. I like to do it in terms of an analogy to gravitational potential energy. That is, if you were to, pull your car up and get ready to go on a hike. So here's the trailhead. You pull up, and you're at some altitude. Okay. Now, when you leave that car, maybe the hike takes you uphill because you're going on a mountain hike, or maybe it takes you downhill because you're going on a canyon hike. As you go along this mountain hike, you go up. Maybe you hit the first peak and you head down into a valley only to get to the main goal of the second peak or even a third peak. So there's some ups and downs along the way. Maybe even you loop around and go down the back of the mountain and come back. But the bottom line is, when you finish this entire hike and you get back to your car, whether it's an out and back hike or whether it's a loop hike, you're going to go up just as much as you're going to go down, because you're going to have to end up at the same height as your car. That is the conservation of energy. And likewise here, there'll be some increases in voltages and some decreases in voltages. And so if we call this point A, and maybe this point B, and this point C, and this point D, and this point E, and F, and G. Maybe I have too many. But if I do this entire loop from A to B to C to D to E to F to G and finish back at A, going around that loop, all of those voltages changes, so the sum of all the voltages should give me 0. So in this case, from A to B would be an increase of voltage of V. Over here, B to C, nothing interesting happens. C to D, there would be a decrease in the voltage. So this would be an R1, I1. And so there's our Ohm's law, and a decrease because we're going with the current. As we hit D to E and then finally from E to F, there's another voltage change. We're going with the current. It's current number 3 and resistor number 3. And then nothing else interesting happens from F to G back to A, and you get 0. So that was kind of a quick summary that I thought I'd throw in here since your author did here at the beginning. But it's the same thing that we've been doing on the homework and the same thing that you guys have asked a lot of questions already by email, and I've done a bunch of video solutions for it. So I think you got that nailed. And so here is today's lab. Today's lab is called Kirchhoffs Laws. The truth is it's a little more than that because we're going to build a bunch of circuits. And in the process of building these circuits, the latter half of this lab is a verification of Kirchhoffs laws. So we will build a circuit that looks a lot like the one I just had, and then we will check out those loops and the current and see if they match. And so that's why I think the thing is titled, or this is titled, Kirchhoffs Laws. But the truth is, and I'll turn the page to page 28, we really don't verify and look at Kirchhoffs Laws until we get to step 5. And so 5, 6, and 7 are really about Kirchhoffs Laws. But the beginning ones, 1, 2, 3, and 4, are just some exercises in the equivalent circuits. And more than that, and this is where, sadly, I really wish this was in class and in phase, because the goal of steps 1 through 4 are saying, can you take a DMM, a digital multimeter, and can you switch it and make it a voltmeter? And then after that, make it an ohm meter. And then after that, make it a, let's see what I say, ohm, volt, and ammeter, okay? and so those are the 3. And then these measure other things too. But those are the 3 fundamental ones and the 3 big ones and the 3 that, in a lab setting, that's what you're designed to do. And in some sense, you guys in the circuits class, this will be old hat to you, because you part of your equipment that you bought for the circuits class was one of these multimeters, and you're constantly doing that. So let me review real quickly. We've seen them over the last couple of labs of how to use this, but this lab, being our last one on circuits, really is the grand finale. And you'll see here, your author, he deliberately plans the next 4 steps to make you constantly switching. It's almost like I look at it and I said, well, wouldn't it be better if I just measured the resistance for all 3 of them right now instead of switching? But I think that's what he wants. I think he wants you to measure it as an ohm meter, switch over, measure a voltmeter, only to go back and measure as an ohm meter, and then measure as an ammeter. And so he's constantly asking you to switch. And since you guys aren't able to do this in class in hand, I'm going to keep showing you. And so I thought that I better start today's lab with kind of emphasizing that not only are the first steps kind of a verification of the equivalence, but they are really more of, can you use a multimeter correctly? All right, so let me disconnect the wires, and maybe to help you out, I'm going to use the orange wires. I'll use the red and the black ones for hooking up the circuits here, but I'm going to use the orange ones for the meter. And just to remind you, we've learned about all of these meters. I'll start with the first one we learned, the voltmeter. All right, now for a voltmeter, this multimeter, number 1, you switch to volts. And number 2, you have to ask yourself, what are the 2 connections do I use? And just as a recap, I'm going to point out that the black connection, the one that says common, is one that I will use all the time. So no matter how I use this, as an ammeter, a voltmeter, or an ohm meter, I will always have a connection here. As we saw before, and just to remind you, this one here that's got the volt and the ohm symbol is used when you are using this as either a voltmeter or an ohm meter. And so I'm showing you a voltmeter right now. Now for the ammeter, you would use one of these connections. Now this one says it measures currents up to 300 milliamps, and the other one says it reads up to 10 amps. Now the 300 milliamps will be fine for us. So this will be our connections when we're using it as an ammeter. But as I said, I want to show you a voltmeter. So I'm going to hook this back to here. Now that this is set up as a voltmeter, let me remind you one more thing. When you go to hook it up, voltmeters are hooked in parallel. So that makes voltmeters actually the easiest thing to do. You already hook up your circuit, and all you have to do is take your two wires and connect them right into it. Okay? And so a voltmeter, I'll say it again, needs to be on the dial V, needs to have two wires here, needs to be hooked in parallel, and the power needs to be on. You're not going to measure any voltage if you haven't hooked up your power. Now, with that said, let's talk about the ohm meter. Because the ohm meter, of course, I would just go to a different setting on here. That would tell the computer I'm on an ohm meter. Okay, so I'll go to the little ohm setting. But the connections are still the same. And the ohm meter you also hook up in parallel. But here's an important difference. You hook it up without any power connected. Okay, so without the power supply. And so when we hook these up, we want to be careful. Are you doing a ohm meter? Are you measuring the resistance? Make sure power is not connected. Okay, are you doing a voltmeter? Okay, well, if you're doing a voltmeter, make sure power is connected. They both have the same connection and they're both hooked in parallel. The dial is different. That's a voltmeter and this is an ohm meter. But that's the major difference between an ohm meter and a voltmeter as we switch our multimeter back and forth. Now the ammeter is the hardest of all of them. I was mentioning that, and so let's see that a number of times as we do the rest of this lab. The ammeter for our setting is way over here, the last one. It says a little a. By the way, maybe I should point out, you probably noticed there were two A's just like there were two V's. But the one that's got a flat line on top of it means use that setting when you are measuring what we're going to call DC, direct current. And that's all we've been doing so far this semester. And so things that have a constant voltage. There are other power supplies, which we haven't got to yet, called AC, meaning they alternate, they change. And that's the little tilde on top, the little squiggle. And so I would put it on that A or that V if that's what I was measuring. So that's why of these two A's, I'm going to go to the A with the flat line above it, just like the V with the flat line above it. Little note that we'll see later on when we start working with circuits that have a alternating voltage or an alternating current, AC. But we're doing only DC. So let me not get too far down that road. All right, now, besides changing the dial here, I also have to change where this one wire is. Notice the common wire is still here. So my setup now would be for an ammeter. And I will point out that an ammeter, in order to work correctly, needs to be in series with that resistor. Okay, the current has to go through the meter. And so you'll see here when I start to connect these up, and then like I said, this is the part that would be nice if it was an in-phase setting, because this would give you a chance to go, okay, now, how do I do this? And it's not hard, but it's worth doing the first time and getting your hands messy, because you're inevitably to do it wrong one time during all these complicated procedures. But as you'll see, I'm going to hook it up so that the current goes in here and then out here, or the other way around. By the way, our meters, it does measure which way the current is flowing, and so it will read a plus when the current goes in this wire and out the common, and it reads a negative if it goes in the common and out what I'll call the plus, if you will. Okay, so we can tell which way the current is flowing, but I think for all the measurements we have for us today, the actual which way they're flowing is not really important, and so I'll just probably pay no attention, and then maybe I'll look once in a while and say, oh yeah, notice it's a plus or notice it's a minus, and make a comment about it. All right, so that was really what I wanted to review and then show you in these next 4 steps. So let's begin. So step 1 on page 28 says this, and you're going to be writing down the values as I kind of do the recording, and there's going to be a bunch of calculations for you to do. So number 1 says this, and I'll just take my book and go to the far side of the board here and see if I can fit everything on one big long board. I think I can, but if I put number 1 here, say what it says is find yourself 4 resistors. And those resistors should be approximately 75 ohms, approximately 105 ohms, approximately 205 ohms, and the last one approximately 750 ohms. So step 1, of course, being the easiest one here, it says simply find them and then use your multimeter as an ohm meter and measure them accurately. All right, so let's hunt for them. And so if it was face-to-face, I would give you these 10 resistors and say, find the 4 of those. Since we're doing the labs in a remote setting, I'm your lab partner. Okay, here I go. I'm going to scan these 5. Ah, there it is. This one says 75. And so remember, the number that is stamped on here is just approximately. It's not exactly. So I'll call this the second one down. Now, over on this board, this one says it's about 105, this one says it's about 102, this one says it's about 750, this one gets a little bit more, about a 3,000, and this one I think it says 7,500, it's kind of hard to read. So it's these top 3 that I would want. All right, so now that I found them, let me start with the 75. Let me point out, let me come over here and set this up as an ohm meter. So as an ohm meter, I set it on ohms, and I put the wires in the 2 right-hand side connections without the resistor hooked to any kind of power supply. I hook it in parallel. And so our resistor is 75.0. So it is not only close to 75, it is right on it. So our first one, and what you're going to write down for the lab here, is our first resistor at 75. All right, now, same idea. If I jump over to here to this first one here, this one said it was near 105. I think I got a little loose connection there. It looks like when I push on it, I get about 105. Let's see. You know what, this wire seems a little flimsy. I know I said I would use my orange ones, but I only have those 2 orange ones. So I'm going to grab another one. Or maybe I'll run over here and grab another orange one. See what happens here. I'll grab a couple of orange ones. There might be more of the board than anything else. And
Another board?
Do you think I should get another board or go with this one? Just in case? All right, let me grab another board here. Oops. It's all dark back here. Ah. All right, I'm back. Sorry, yeah, course, normally we get out a bunch of boards for a full class here, but in this setting we just got out one board and seemed to be one that wasn't the best. All right, so what? I still wonder if I'm going to grab a couple, see if I can find a couple of wires that feel like they're a little newer. Yeah, maybe. All right, so let me go with this. Looks like 105.5. Okay, so 105.5 ohms. And let me go to the 205. Actually, I think I would feel better if I made both of these wires the same length and kind of long so that I can just kind of hook up my meter separately at the end. Okay, so this is 206. 206.0. And then finally, the fourth one here, and this will give us some numbers to work with. This 750 is 751. So 751. So that's really the point of step number one, is to figure out what the resistance is of our resistors so we can actually then start, as I said, doing some equivalents here. All right, so here's really kind of where the verification of our circuit stuff was doing, and also going to test our ability to hook up a multimeter. Number two says this: connect any of the three you want in series. Measure their equivalent resistor and compare it to theory. Note, in calculating the theory one, be sure to use the values that you just measured in step one, since the measured value may be a little different than what's stamped on it. All right. Then connect it to a 6-volt battery. Connect a 6-volt battery together with these series 3 resistors and check its voltage. Terminal voltage, now that it's drawing a current, is still 6 volts. Use this voltage to calculate the current through each resistor and the voltage across each resistor, and compare this to the measured values. Here's what it's trying to say. All right, so it's saying do something like this. Take any 3 of them and hook them in series. And I don't know if you noticed, but these 3, 2, 3, and 4, are all in the same board there. So I'm just going to make the call. I know that we're working as lab partners here, so I should probably say, hey, which 3 do you want to use here? But obviously somebody has got to make that choice here. So I'll make that choice. So I'm going to pick the number 2, number 3, and number 4. Those are the 3 that I'll just put in series. And here's what it says. It says figure out what the equivalent resistance is as you measure it, but also get the equivalent resistance as you calculate it, and see if they match. Okay, so here's what I'm going to do. I'm going to have you guys do the calculation. Okay, how do you get the equivalent resistance when they're in series? And let me not give that away, because I think you know that. I'm going to trust you've known that, but we've been doing it for a couple of weeks now, or this will be the second week of doing it, so just in there. But go ahead and do a calculation. I'll go ahead and make the measurement and write it down, and these two should agree. And if they don't agree, then either we're doing something wrong with our calculation, or we're doing something wrong with our hookup and our meter. I hope that's not the case, because that's the half I'm doing. I'm going to go and do the measured value. You do the calculated value. And if they agree each other, then you could move on. And so in a face-to-face setting, that's what I would say. I would say this is kind of a test. If they agree, move on. If they don't, you're doing something wrong. Let's learn what it is, and then we'll continue. All right. So, like I said, you do the calculation. Let me now do the measurement. Now, as we already pointed out, I already have my multimeter hooked up as an ohm meter, so I'm just going to set it to the side. In fact, I'll even put this circuit board to the side, because I want this then in series. And so here is resistor, what I've called number 2. And so why don't I do something like the following. I'll say we'll start here and go through number 2. So this is the end of number 2. And then that's the beginning of number 3. Okay, then it goes through number 3. And from number 3 goes to number 4. And then that would be the end. So this is my series connection from here to here. And just to remind you, because that's part of the big thing of this lab, is to use an ohm meter. We want to make sure this is not connected to power and it is hooked up in parallel using the 2 right connections and the dial on the ohms. So I've got all of that once I do the following. And so I get an equivalent resistance of 1062. So 1062. Let's see. And if I were to add these 3, oh, and I said I wasn't going to do it, but it would be nice to 11, 12, carry 6. So apparently my measured value is going to match what you calculate really well. Okay. Oh, and I should probably put ohms up here, Ron is saying. So, sorry I couldn't resist actually doing the calculation. I need to stop that though, because that's the half I want you to do. So I'll do the measurements, you do the calculations, let's see if they agree. All right, now there's a lot more to this problem. Then it says, after you've done this, and so if they agree, go to the next step. And the next step says to hook this to a 6-volt battery. And when you do, there will then be a current in number 1, and a current in number 2, and a current in number 3. A voltage across number 1, a voltage across number 2, and a voltage across number 3. And so you are asked to make a measurement of each of these and do a calculation of each of these. And I would say in a face-to-face setting, if what you measure and what you calculate don't agree, you're doing something wrong. So let's figure it out, and before we move on to the next harder step. And so these 4 circuits, well, maybe I shouldn't call that a circuit, but the next 3, step 2, step 3, and step 4, are just like this, where they get a little bit harder. And then, of course, then we get even to harder ones with Kirchhoffs laws. And so if things don't agree with our calculation, we're doing something wrong. And so this is a good lab. I know in a face-to-face setting, it tends to be kind of a long lab because students are like, ooh, I did something wrong. What is it? And they're kind of hunting around. But it's a good learning opportunity. All right, so here's what I'm going to ask of you. I'm going to ask you to go ahead and do a calculation. Calculate the current in each of the 3, calculate the voltage across each of them, and I want you to fill those in. And they should match what I measure, unless one of us makes a mistake. And like I said, hopefully it won't be me. If I do, and you're the first one to discover it, please let me know so I can let everybody know that I made a mistake. Okay? So let's give it a try here. All right, so first of all, as you've heard me say a few times, that I like to think of my meter as, you know, a measuring device. So I like to put it off to the side. In fact, this will be the side. And so I can hook up my circuit. All right, so I turned the power supply on before the filming started and adjusted it to 6 volts. Let me just double check. Yeah, it looks like it went back to 6 volts. And so if I grab a couple of red wires here and hook this to the 6 volts, and following the order that I've drawn up there, it says hook the power to number 2 first. And of course I already have it hooked then to number 3, and then in series to number 4, and then to finish the circuit from number 4 back to the negative. And your author even says just double check that your voltage is still 6, because once we hook it up we can start drawing current and it may change, but I must admit that's kind of old school. These newer power supplies that we have, they're really good. They don't have much internal resistance, and so if it said 6 without current and you hook it up and you have some, at least if you're not over blasting the current, it stays at 6. And so sure enough, it's still at 6. So that's why it says check the terminal voltage now that you're actually drawing current, and not just the EMF as we did in the last lab, or 2 labs ago. All right, so now that I have it hooked up, I can go ahead and make my measurement. And why don't I do the voltages first? Oh, you know what? Probably bad notation on my part. I apologize. Just to keep this going with the 2, 3, and 4, let me continue to go with 2, 3, and 4. There is no 1, because 1 I would call the current in this one, which I didn't even use because they said only use 3 at this point. So presumably, just to keep my notation consistent, I'm going to have the other one later on. So I'll just want to be a little careful here. All right, so changing the notation a little bit, why don't we measure the voltage? The voltage across number 2, the voltage across number 3, and the voltage across number 4, because as I said, that one's a little bit easier than the ammeter. So let's come back to our voltmeter, or our multimeter I should say, and let's set it up as a voltmeter. As I said, the knob has to be pointing to the V, and I need to plug it in to the right connections, which in this case the right connections are the 2 on the right. The common one is obvious, and then the one right above it's got the little V on it. Okay? And the reason the voltmeters are easier is there's really nothing I need to mess with in terms of the circuit. You hook it in parallel. And so if you just kind of put the wires right there on top, boom, you get the voltage. Okay? Now notice I didn't pay attention to which one was the red connection and which one was the black connection. I do have a negative sign. I'll mention that in a minute, but it says 0.599. All right. So I have a 0.599, and the units are in volts. Now just to point out here, as long as I've got your attention, mine does say negative here. And just to, again, the computer on here reads positive when this connection is greater in voltage than the black one. And it reads negative when it's the other way around. So that would tell me the black connection, the common connection, is at a higher potential. And if you look at the way I connected it here, if I would come into here, I've got my black connection here and my red connection here. So this is saying this is at a higher potential than that one. And that makes sense because this is the 6. So it's going to go down and then down and then down and then around. Now, if I answered this in terms of Kirchhoffs laws, you would say, well, that's pretty obvious, right? This has got to go up and then these go down. This is sort of like our hike. We park the car, we get out, and the first thing that we do is we go up the hill. Then we go down a little bit, and then down a little bit, and then down a little bit before we get back to our car. And so there's 3 kind of downward hikes, if you will. And so we go up 6. So this and then this and then this should add up to 6, which is part of our Kirchhoffs law, which hopefully we'll see here. So this is down a little bit, and it looks like it's not even 1 volt. It's about 0.6 of a volt going down. But what I was trying to point out is that it's very clear that this is higher than this one, which is why I got a negative. In fact, as long as I've got your attention on it, maybe I'll just switch it around and put this one here and this one here, and you'll see that in terms of absolute value I have the same number, but now I have a plus sign. All right, well, let's go to the other resistor. We called it resistor number 3, and so let me put that one here and that one here, and I've got it set up so I should get a positive reading. So sure enough, I get a positive reading and I get 1.173. So 1.173 for the volts on resistor number 3, or across number 3. And then if I move the wires to resistor number 3, I get the voltage on the last one, the bigger of the one. This is the biggest change, and this would be 4.27. All right, so I'll say it again. I've done the measurements. Your job now is to do the calculations, and hopefully they will be within reasonable agreement. Okay? So now let's do the other half of our measurement. And this one is the hard one, which is why I kind of saved it for last. But we're going to do this a lot today, and we need to measure current. So I'll say it again. To be an ammeter, I want to put my dial all the way on A. And the 2 connections I want are, and I'll just say it again, obviously the common one. That's always going to be the case. But this one here that says it can read current up to 300 milliamps. Now I know I haven't done any of the calculations. If we were in setting, I would ask you do the calculation first to make sure it's under 300. I know from experience that all of our setups are way under 300. Although, that being said, sometimes things can be hooked up wrong. And then we've got a fuse inside. In fact, the fuse, blows when it gets hooked up wrong. In fact, I probably should have tested the fuse before I started the video camera here to make sure it was not a blown fuse. But I guess we're going to find out right now. Okay, so here's what I like to do. This kind of helps my thinking. I just like to kind of put the ammeter off to the side, and I hold kind of both wires in one hand. Because if I want to measure the current, say, coming out of resistor number 2, I find resistor number 2, so there it is. So the current would be going in here. And right here where it's coming out, I literally just disconnect it and then plug it into one of my wires. See, that's going to feed it into the ammeter. And then I make sure that I then put the other wire back to where it was going so it can still be going through the rest of the circuit. And in fact, if I was drawing a picture, I would say this is what I've just did. Right here, I opened it up after resistor number 2, and I fed that into the ammeter. And at the other end of the ammeter, I hooked back up to where I had disconnected it so that it would keep going into resistor number 3. Now I didn't pay any attention to which wire was which, but it looks like I have set it up so that the current would come, let's see, out here. And I think I used my words backwards. I apologize. I said this is going back. This is where it comes out. So it comes out here, goes into the meter, through the meter so it can count it, and then around, and then goes back to where I had disconnected it. Okay? And so since it goes in here, I should get a positive reading, I do. And then this would be my reading in milliamps, and so 5.61 is my measured value. So, ooh, bad notation up here. Maybe I'll put it here, volts, volts, and volts. And then this is 5 point, so what did I say now? 5.61 milliamps. And of course, now that you've gained some experience with this, you know, hopefully, if you kind of look at Kirchhoffs laws here, I didn't actually, you know, add these together, but I did make a comment that these should add up to, and it looks like it's going to, 7, 8, yeah, 7, 8, yeah, just going to be okay. But also the other thing about Kirchhoffs laws is the current one, and there's no place for the current to go other than into resistor 3 once it exits number 2. And the same thing, once it exits number 3, it has no place to go but to number 4. So I'd be very surprised if either my calculation or my measured values of the current gave me anything different. So that'll kind of give me a running test here, and so I'll give it a try here. Watch. Let's look at the current that is coming out of number 3. First, let me put it back together. So what I'm going to do is disconnect my ammeter and put the circuit back the way it was. Okay. Now I'm going to grab my 2 wires and see right here where it's coming out of number 2. I'm going to disconnect it. And I'll say it the right way this time. I'll put my meter there. So now it goes to the meter and then goes back to the circuit just like it was before. And so what it's doing is it's coming out of number 2, going into the meter here, circling around, number 3, sorry. Yeah, number 3, the second one in my circuit. Okay, so resistor number 3, coming out of number 3 to here and then back again. And so this should give me the same number, or at least very close to it. And so I get 5 point, and it looks like there is some variation in my reading for a number of possible reasons. Could be how well I got them connected together, a slight amount of resistance changed. Could be the fact that our meters, you know, don't read perfect, and so we'll see what we have here. Looks like I already got a better change. What happened? Did I push that harder? Okay, but you can kind of see that depending on how contact I have, and sadly that's what happens to our meters. We have them sitting around, they get little dust on them, and so they, you know, sometimes I say, go ahead and just kind of rub the connections here and kind of work that dust off that builds up. All right. Oh, and this is one that matches a little better. Yeah, so I like that. However, I'm not convinced that this one was such a great one because I didn't scrub off the dust on that one either. So who knows which is the better of the two. But they're so close that I think I'm able to move on. And again, hopefully your calculations are very close to that. And so let's do one more on this step here. And so again, let me disconnect my ammeter and hook it all back together and do exactly the same. And last part of this, I will disconnect it from resistor number 4. I will feed that into the meter, then from the meter back to completing the circuit like it was before, and it would be flowing through. And it looks like I switched my wires. I got a negative reading. Let's just check. Yeah, see, look, it's coming in this wire here, which goes in the common and out here. So I got a negative reading, but not paying attention to the negative, I got a 5.60 here. And sure enough, I feel pretty comfortable with these 3 readings because just looking at the circuit, I know that they should be the same. So without taking away your fun to do the calculations, even though I am tempted, I find it hard not to finish the problem, but I could calculate those, and so I want you to do that. And so hopefully what you calculate and what we together measure agree, and now we can move on to a harder one. All right, so on to a little harder one here. Number 3 says the following. Number 3 says, connect the 105 and the 205 in series with each other. Let me just kind of draw that. Okay, so here I will take the 105 and the 205 in series. So the 105 I've labeled as R2, and the 205 I have labeled as R3. Okay. So connect the 105 and the 205 resistors in series with each other, and this in parallel with a 750. Okay. So this grouping of these two is then going to be in parallel with resistor number 4, the 750. So maybe I'll just make a connection like this. And the instructions, if I can save some time from reading it, are exactly the same thing that we just did in step 2. And that is, number 1, go ahead and find the equivalent resistance both by a measurement and by a calculation. So I'll let you calculate the equivalent resistance, and I will hook it up and do the measurement, and hopefully they agree, so we can then move on to the other part, which is to make a table kind of like this again. All right, so let me do this. Let me come over here and disconnect my meter. I always like to kind of think about that last. I could even disconnect my whole circuit here. So here's my power supply off to the side. That's probably a good step too, because remember, when you want to make an ohm meter, you got to be disconnected from your power supply. All right, and so that's what I'm eventually trying to do. So disconnecting from my power supply. And so let me come back here and put number 2 and number 3 in series. So this is essentially what I had before. So here's number 2, here's number 3, and series would look like this. We would start here at number 2, go through it, loop around, go into number 3, and so this right here would be this connection, and this right here would be that connection. Okay? And now we want that in parallel with this one here, number 4. So let me do this. Let me take this connection and hook it here. And so it would look something like this. There's the beginning of the 2 in series, and there's the beginning of the 750 ohm resistor. So this wire right here is this wire. Okay. Let me grab another wire here and say, okay, now on this side, the end of the 3rd resistor and the end of the 4th resistor are to be connected. So there's the end of the 3rd, and there is the end of the 4th. So this wire right here is this drawing right here. So I think I've done it right. Like I said, this is kind of the fun part in the lab when you're here face to face, is, you know, you guys are hooking this up, and if you don't hook it up right, well, then when you measure the resistance, it doesn't match what you calculate, and you know that. And so you pause and you go, okay, let me figure out what's going on. All right, so I think I have the circuit. I'll kind of hold it towards you here, and then I'll come over here and just remind you, I got to get an ohm meter. So an ohm meter goes to the ohm setting. It goes to the 2 connections on the right. It is connected in parallel with no power. All right, so I have no power, and I have in parallel. All right, so as we said earlier, this wire right here is this connection. All right, so I've got that. And this wire over here is the connection here, and so I'll plug into that. And so I get a reading of 219.9. So 219.9 ohms, and this is where I'll let you do the calculation. And as I said, hopefully what you calculate and what I measure agree, so we can move on to the next step. I'm going to trust I did it right, because I don't really have anything to verify it with, because I'm going to save the calculations for you. And then I'll go on to this chart. So let's make this chart again. And so what is the current in number 2? What is the current in number 3? What is the current in number 4? What is the voltage across number 2, the voltage across number 3, and the voltage across number 4? Okay. And then let's, as we did in the last one, let me do the measurement with you here on video. And then, of course, you are going to do the calculation. And so this will be kind of our test to see if we're calculating and measuring things correctly. If they agree, then we can move on to number 4, a little harder one. All right, so like on these other ones, I'll do the measurements, you do the calculations. All right, so let me disconnect my ohm meter for just a second and move it to the side, because I'll add to my picture here what we're asked to do, like before, is then to hook it to a 6-volt power supply. Okay, so I'm going to hook it to a 6-volt power supply. So here's the 6-volt power supply. Here's the plus. Here's the wire that connects the beginning of this circuit. And then here is the negative. This would be the wire connecting the end of that circuit. All right, so I've got the circuit hopefully connected correctly, and now I can make my measurements. And I think I'll do the same thing. Since the voltmeter is a little bit easier, let me do that first. And so I'll put it over here on the voltmeter. I've already got the connections in the right place for a voltmeter, because I just came from an ohm meter. And then I just have to hook them in parallel. And so if I wanted to know the voltage across number 2, I just literally plug it in on both sides. I don't have to disconnect the circuit. That's why voltmeters are so much easier. You just clamp on. You don't have to open up the circuit and hook them to go through, the electrons to go through, which is what makes ammeters a little harder. All right, so according to this, I have 2.045, and so 2.045 is the voltage across number 2. And then over here, and I want to put my units here, volts, okay. And then over here, I'll put the 2 wires and go across the resistor number 3, and I get 3.99 volts there. So basically a 2 and a 4, which add to a 6, and so I'm feeling comfortable about that. If I look here at, again, kind of the Kirchhoffs law here, if this is 6 volts and you look at a loop, starting over here, I'd go up 6, and if I followed this, I'd have to go down a little bit and down a little bit more. So that means these 2 down should add up to that 6. And so sure enough, the down here is down 2, and the down is 4 more, and so that is a total down of 6, okay? So I feel real comfortable with that, okay? And a little bit more. I'm not, this is 6.0. Maybe I should have hooked up the meter and got some extra decimal places to see how close I was to 6. Because this might be a hair more than 6. In fact, as long as I have it as a voltmeter, got me curious here. I'll hook it to here and here, and so it's 6.04. Where's the fine adjustment? Oh, I probably shouldn't change it now in the middle, huh? So I'm going to be a slight variation. So by the way, if you wanted to do a calculation back here with 6.04, these might match up a little bit better. And the same thing here. Yeah, see, actually 04 would be perfect for that, right? That's going to be 6.04. Although now that I changed it, now it should be 6 for the rest of the lab. All right. So if I come over here and I do the third one, and so I'm sorry, the number 4, but the third one of the measurements we have to do. But resistor number 4. This is the voltage across it, and it looks like it's 6.00, so 6.00 volts there. Now again, if you came over here to Kirchhoffs Law, I'm not, too surprised and feeling really good about this, that if you did a loop that would go up 6 and then take this path, you must go down, and it's just one big step down, so it must be 6. And so sure enough, I'm going down 6. Yeah. Or 6.04 if I had left it there. All right, so I'll say it again. Those are the easy ones. You are to calculate them, and hopefully what you get here is the same numbers, or close to the same numbers that I got there. And if you want, you could calculate these based upon 6.04 and these on 6, and I changed it in the middle. But not worrying about that many decimal places, they're going to agree. Okay, so now the harder one of this measurement, as I keep saying, is the ammeter. And so let me switch it over to an ammeter. And like I was trying to show you, what I like to do is just kind of grab the two wires. Oh, let me change the connection on my wire. Remember, the ammeter is the one that needs to be, of course, the common, but it needs to be over here at the 300. And again, I haven't done any calculations yet, but I know from experience that all of these should be under 300. And so unless I hook something up wrong, we won't blow the fuse on here, the little safety device here. All right, and so I'll do the same thing that I did before, is I like to do this. This is resistor number 2, and so if I disconnect it and say, okay, come out of there and go to the meter first, but then go back so that everything is still the same. The only thing I change is I'm now feeding it through and into the meter here. I should get the current that goes through here, and it looks like I have an 18.64. And maybe as a side note, I'll point out that notice it's saying negative. So I didn't pay attention, but the current should go through out here and then in here and then this way and back. So yeah, should be a negative reading because I've got it going into the common one first. And so this is reading a negative current. Oh, and milliamps. Yeah. Oh, I guess I don't need brackets and it's there. Okay. And so again, in this drawing, I guess I would say what I've done, just to kind of keep helping you with this ammeter, is I have opened up the circuit right here at the end of resistor number 2, and I have put the little ammeter there, so it's got to go through the ammeter as it goes into resistor number 3. And so what I'm about to do would look something like this. I'm about to look at what comes out of resistor number 3. And of course, hopefully, we're using Kirchhoffs laws here. These are all in series. So hopefully the current that's going through number 3, and so the reading on the ammeter will be the same 18.64. Let's see what happens here. Okay, so I will disconnect the ammeter. Okay, and do it all over again. Okay, so number 2 is coming out right here. So I'll disconnect it here and put one of my wires in there, so it's coming out of number 3, and then I'll feed it back in to the circuit where it just came out of, and so this is what's coming out of number 3, and 18.64. Good. And so 18.64, as I kind of suspected. Milliamps. And milliamps. And so the current looks like it's coming out, and then it looks like it's splitting here. This is this 18.64 milliamps. Of course, some of the other stuff is going down this bottom branch. And so that I would expect to be different than the 18. And you could even then calculate what it could be. That's your job, so I won't. But I will then put the circuits back together first. Okay. And then I will get to resistor number 4 down here, and I'll just kind of unplug this right here. Okay, so there's resistor number 4. So what's coming out of resistor number 4 is going to go into my ammeter first, and then after it goes through my ammeter, it completes the circuit. And so it looks like I got a 7.5 0.85 milliamps. And again, as tempting as I am to calculate these, that's your job here. So go ahead and calculate them, and this will give you kind of a test. And then again, the idea is if these things match, move on to the next step. That is, you're hooking them up right and you are calculating them right. And so we can go on to a little harder one. And so each step they get a little harder, and perhaps we learn a little bit more as we gain more experience. So let's try number 4. Number 4 says this. It says connect the 205 and the 750 in parallel with each other. Okay, so the 205 and the 750 in parallel with each other. So we call this number 3 and number 4. So number 3 and number 4 are in parallel. Okay, so the 205 and the 750 in parallel with each other, and this in series with the 105. And the 105 we've been calling resistor number 2. Okay? And that completes this circuit. And again, we're asked to do the same thing. So let's go ahead and find the equivalent by a measurement. And so we'll do that together here. And then go ahead and get the equivalent with a calculation. That's what I'll leave for you to do. And so those two should match. And if those two match, then we can move on and hook it to a 6-volt power supply and fill in this chart that says what is the current in number 2, what is the current in number 3, current in number 4, voltage on number 2, voltage across number 3, voltage across number 4. And so we will finish up the first half of this lab with our equivalencies here with one more step of just verifying that our hookups and calculating things match. And so our calculated values match our measured value. All right, so I have a whole new circuit to hook up here, so I kind of maybe just want to start all over, although there are some parts of this circuit that might be nice, but I'm going to go ahead and just start all over, and particularly disconnect the power supply and use this as another opportunity to point out that for an ohm meter you want to be disconnected from your power supply. All right, so if I grab a couple of black wires here and I come over to this picture, and again, okay, this is number 3, this is number 4. It says 3 and 4 are to be hooked in parallel. So there's the beginning connection for 3 and 4, and then there's the end connection for 3 and 4. So this wire is that drawing, and this wire is this drawing. Now, if you then think about it in that fashion, this wire right here then gets connected to the beginning of number 2. So here's number 2, here's the beginning. So I'll say this wire right here gets connected to the beginning of number 2. And so if I've done this right, this wire right here, as I said a moment ago, is this one. So this is the beginning of the whole circuit. Then goes through these two, and they're connected together, then loops around and goes to resistor number 2 and goes through, and so this right here is this final connection. And so that means that if I set this up as an ohm meter, so I'll take my multimeter, I will set it up as an ohm meter, say it again, put it on ohms and the 2 connections on the right, and to use an ohm meter correctly, not hooked up to power, I will then take right here the beginning of these 2 in parallel, which is number 3 and number 4, and then it'll exit resistor number 2 right there. And so this says the equivalent is 266.8 ohms. So 266.8 ohms. And so you need to take a moment right now and do a calculation and see if they match. Okay? And so that's my circuit. All right. So if that worked well, I'm going to come over here and then hook up my 6-volt power supply. Maybe in my drawing I should put it up here and say, okay, here is my 6-volt power supply. And once we hook it up, we will now have current and voltages in each of these resistors. And your job is going to be to calculate them. And I guess our job together here is to figure out how to hook them up and make the measurements. All right, so here's the power supply, here's the plus, and looking at that picture, the plus goes to the beginning of the 3-4 connection. So that was this wire. Then it loops around and comes over here and exits the resistor number 2, and that completes the circuit. So now let's make our measurements. And as I have mentioned a few times, I think the voltmeter is a lot easier, so I'll just go ahead and hook it onto a voltmeter, because for a voltmeter you just hook it in parallel right across it, and that's easy to do. You don't have to mess with the circuit in any way. You can just come up and start plugging things in and measuring it. So I'll do this number 2 here and say the voltage here is 2.366. So 2.366 volts is the voltage across resistor number 2. And if I then go to resistor number 3, again, just plug it into both sides of resistor number 3, I get 3.63. 3.63. Now, I don't know if you're thinking about Kirchhoffs laws here, but I just did 2 and 3. And if you look at this loop, this would be, you know, if you were going on a hike, you'd go up here a little bit. So you go up 6, then you would go down and then down some more and complete it. So these two together should add up to 6. And I think I'm pretty darn close to that. There's the 5, there's the 9, yeah. And so they add up just right. So I feel comfortable with that measurement. Now my other measurement is the voltage on resistor number 4. And I'll just point out that we started this by saying 3 and 4 should be in parallel with each other, and we know that parallel has the same voltage, so hopefully I get a 3.63, and I do. And so 3.63 volts would go there. All right. And like I said, your job is to do a calculation. So hopefully your calculations match my measurements and we can move on here. Now, before we kind of change into a more complicated circuit here, let's do the hardest one of the measurement, which is the ammeter. So let me switch the dial to the A for ammeter. Let me change the connection of where the wire is, and let's just then hold these two in our hand and do something like this. When it comes out of resistor number 2, I can then feed it into the meter and then feed what comes out of the meter back into what I just disconnected, so it completes the circuit. Although actually I did it as it's going in, not coming out. So that's a little different than the other ones, but hopefully you're good with that, because this is what goes in is also equal to what comes out of the resistor. I've been used to doing this side because that was out, but if you'll notice, I put the positive here and then it arcs around and then Oh no, and then comes out. Oh, I did. Oh, never mind. I did. Okay. I said that wrong. All right. So anyway, it doesn't matter whether it goes in or comes out, but what number do I get? And so this says 21.80, and 21.80 milliamps then is the current. And like I said, hopefully you're doing a calculation right now, and your calculation is going to be somewhat close to that. All right. So disconnecting my meter and hooking everything back up. Okay, good. Let's look at resistor number 3. All right, so it would be coming out right here. So I'm going to disconnect where it comes out of resistor number 3, feed it into the meter, and of course after it goes into the meter it would continue on. So I got to make sure I make it continue on. And so this is 1717. Now hopefully you'll notice those two aren't matching, but again I think you can sort of see that what's going to happen here is number 2 was what happened after the current came in and divided here, going from 3 and 4 and recombined. So I would expect them to be different between the 3 and the 2. And I would also expect 2 to be greater than 3. And sure enough, that's what I have. And of course it's greater because the current that's going down through resistor 4 and re-merges with what separated off originally, this bottom one then must not be all that big because number 2 is bigger, but really not by that much. And so let's see what we get here for our final reading here. And so we'll disconnect and put it all back together. Okay, hey, welcome back. We had a little power failure there, so I'm not sure exactly where I was, but I think I was trying to get the current here for number 4. And so I put the circuit back together here, and I've got my ammeter. And since I was doing some troubleshooting, let me turn it back to an ammeter. Okay. And so there is my ammeter. Common? Yeah, I'm on common.
Are you?
Yeah.
Wait, I'm sorry, I saw one.
Okay. And so here's my ammeter. And let me go ahead and get current number 4. So number 4 would be this. Coming out of here, going into my meter, and then back. And I think I said right before we lost power that this should be a small number because it's combining together. And sure enough, 4.77 seems about right. And 4.77 milliamps seems good because it's these two merging together that gives me number 2. And so 3 and 4 merge together to give me number 2. And so that's looking real good. Add those two together, I get that. So I'll say it again. This is where we're going to switch gears a little bit, get to a little harder one. Still working with circuits though. But all of these that we've done so far really could be done by doing an equivalency. Of course, you could also do them with Kirchhoffs laws. But the next one is deliberately designed a lot like your homework one that you guys keep sending me email questions on. And when we Zoom on Friday, saying how do I do these? Because yeah, they are harder, and you can't make the equivalence. You've got to just write out. And you know, some of the ones we were doing on this last Friday had 5 equations and 5 unknowns. I think this one coming up has 3 equations, 3 unknowns. And so I'll encourage you to get out the calculator as I was showing you and set up your matrix and do the RREF to solve it. But I'm getting ahead of myself. So anyways, your job here in step 4 is again, do these calculations and see what you get. All right. So I'm going to jump way back over to here. Maybe I won't completely erase number 1 in case I need to come back or you need to come back and look at those numbers here. But now let's do numbers 5 5, 6, and 7. And you'll see they're kind of all tied together. But it's the same idea that you're going to hook up a circuit and you're going to make some measurements and you're going to do some calculations. And hopefully what happens is what you calculate and what we together measure agree. And so let me begin here with number 5. So number 5 says this: verify that. Oh, I'm glad I didn't erase number 4. Actually got ahead of myself here. Number 5 does tie back into here. Sorry about that. Number 5, it's actually kind of hard, I think, to understand. It's actually a pretty easy problem, but kind of hard to understand what the author is asking. Number 5 says this: verify that Kirchhoffs are valid for the above circuit. And so what he means here is verify that it does work out, Kirchhoffs laws do work out for this circuit. So if you take a look here, I don't know if you can see 3 loops here, but let me see if I can label them. If I call this point A, and this point B, and this point C, and maybe this point D, and maybe this point E, and maybe this point here F. If you take the sum of the voltages around the loop, and why don't I do a big loop from F to A to B to C back to F. So F, what I say, to A to B to C and back to F. The sum of those voltages should be 0. And so we have the measured voltages, we have the 6 volts. You would see that you would need for this calculation not just the 6 volts, but also the voltage on number 3 and the voltage on number 2. And so that should give you 0. And so all I want you to do is write it out. You're not solving for anything, you're just writing it out. So you're going to get like a plus 6, then a minus 3.36, then a minus 2.366, and what does that come out to be? Okay, do that for another loop, and the second loop you have maybe would start at F and go to A, F and A, but now we would go down to the lower part, and so that would be E to D back to F, and again, don't calculate anything, just put in the numbers you've measured here from number 4. So that's what he means by verifying it. You might have done these already when you tried to calculate what they were, but that's not what number 5 is asking. Number 5 is asking, put in the values for voltages here, together with the 6 volts, and do a loop and see if you get 0. And the other loop, the last loop here, is the loop, kind of just this little tiny thing here that includes resistor 3 and resistor 4. So maybe I will call that loop B, C, D, E, back to B. And of course there's just 2 voltages. There's the voltage of number 3 and voltages of number 4. And so you're just going to add those 2 together, but one will be positive and one will be negative and see what you get. And obviously that one I can do in my head and come up with 0. So just put in the numbers and see if you get something close to 0. That's the idea. But it also says this, that pick the node, and so right here where these come together, I'll call it N. Take all the currents that are going in, so the sum of the currents going in to that node, which obviously is the current from number 3 and number 4. So here they are, these 2 are going in. Add those together and ask yourself, does it equal to the sum of all the currents coming out? And of course, in this case, the only thing coming out is the current that flows into number 2. So it'd be that one. So this number would go on the right-hand side. These 2 added together would go on the left-hand side, and just see how if they're equal. They won't be exactly equal, but they'll be close. Just like the loop won't give you exactly 0, but they'll be close. And so take the measured values, not the calculated values, right? This is how you calculated them, okay? But I didn't do the calculation, but you should have done this all to do this calculation. But what you were to do is to take our measured values together and confirm that. So I'll let you look at those 3 loops and the 1 node and see if it's true. All right. Let's go to number 6 then. This is the one I was kind of getting ahead of myself and was thinking about. This is the hardest one. And 6 and 7 kind of go together. But number 6 says, hook up this circuit here. Okay, so let me find my good battery somewhere. But it says hook up a 6-volt power supply and feed it into resistor number 2, but also take a voltage that is roughly 1.5. Now let me point out from last week's lab, 2 weeks lab, that these batteries are not exactly 1.5. So if we want to do some calculations, we better find out what it is. So I'm just going to put for a moment approximately 1.5, but after I hook it up, I'll actually get my voltmeter out and have a number so you can do some calculations. All right. So take a voltage of about 1.5, and then of course find out what it really is, and so we'll do that in a moment, and hook it up to resistor number 3, and hook those 2 things together in parallel, and then also hook that in parallel with resistor number 4. And so, as you can see, none of these are in parallel, right? Because the batteries in between those 2, they kind of look like they might be in parallel, but they're not because of that extra battery. And none of them are in series. And so this is the case, the harder case where we can't do equivalency. This is neither series or parallel, and which is fine because we can solve it with Kirchhoffs laws. Okay. And so if we call this current in number 2, current 2, and we can say it comes down here, the currents would split and some of it would go down here. I'll call it current number 4. This is the hard one to know. Is this battery strong enough to then force the current opposite of battery I'll call this battery number 2, and so it essentially is charging this up? Or is this battery strong enough to overcome it? Now, first you'll say no way because there's only 1.5 to 6, but remember this 6 volts got to go through that resistor and then through that resistor before it gets here. So it could lose a lot of voltage to get there and be under 1.5 and not win the battle. And so a little current could go this way. But given that this is way higher than that, I'm going to just make a guess that the current does go back in this direction, and so we are going to be charging that battery. I don't really know if that's true or not, but that's why we're going to solve this and find out. And so step number 6 says, set up the circuit as shown and measure the terminal voltage. Then use Kirchhoffs laws to calculate each of the current. So your job right here is to find by calculation the current in number 2, the current in number 3, and the currents in number 4. Okay? And so I'll say it again, you can't use equivalencies, you got to use Kirchhoffs laws. And I could have left it for you to decide which way the currents are going, but go ahead, please. And when you do your calculation, use my definition of the currents. We'll find out if my guess was right or not. I'm quite sure that my guess for current 2 and current 4 are right. I can just tell those. There's no question about those. But there is some question in my mind about number 3, whether number 3 will come out to be a positive or a negative. But like I said, my guess is that it will be charging this battery. Now, of course, you can't do these calculations unless you know the voltage of this accurately. So let me hook it up and measure that voltage. All right, so coming over to here, and disconnecting my meter, putting that off to the side, and maybe disconnecting everything. By the way, as a side note, you'll notice that they did not say measure the equivalent resistance. There is no way to calculate the equivalent resistance using series and parallel. So they're not even going to have us mess with that. But they are going to have us hook up a pretty complex circuit here. And so let me start with the 6 volts. So the positive on the 6 volts is supposed to go to resistor number 2. And then if I follow that right, resistor number 2 splits. It goes to resistor 3 and to resistor 4. Right? So I'm going to grab 2 wires here and hook them together. All right, so it goes to resistor number 2. Once it goes to resistor number 2, it can split, and one of them is going to go to resistor 3, and the other one is going to go to resistor 4. Now I'll just look at resistor 4 up here. The one that goes to resistor 4 continues on to the negative of the 6 volt power supply. All right, so that would be right here. And then just double check. So it goes from the power supply through number 2. Number 2 loops around and goes through number 4, loops around and goes back to the negative. Good. The middle branch, if you will, is resistor number 3. So it goes from the 6 volt power supply through resistor 2, from resistor 2 to resistor 3, and then resistor 3, here we go, if I follow that picture, resistor number 3 goes to the plus on this battery that's approximately 1.5 volts. And then, looks like I'll need another wire here, but then the negative of this second battery goes to the negative of power supply number 1. Okay, so I think I have it connected correctly, and now that I have it connected correctly, let me make a voltmeter. So I'm going to switch my DMM to a voltmeter setting, and I am going to then connect my 2 wires in parallel to this battery so I can get its terminal voltage, and it looks like it's 1.568. So 1.8 is the number you're going to want to use in going to ahead and do, a calculation. So I'll say it again. Step 6 is all about you. There's nothing really for me to do here in step 6 other than hooking it up so that I can measure this voltage so you know what the voltage is so that you can then do your calculations. But number 7, and the last step here, other than the discussion questions, is to go ahead and get your meter out and measure the currents in each of these. And of course, hopefully, if things are going right, what you measure here in step 7 matches what was calculated in step 6. And if they don't, we need to fix it. Again, hopefully I won't hook up anything wrong so that when you do your calculation, if they don't match, you can redo your calculation until they do match. Although if I make a mistake, it'll drive you crazy, but hopefully that I won't here. All right. So my circuit looks good, and so let me go ahead and disconnect my voltmeter. And let me switch it over to an ammeter. And like you saw on all the other circuits we were doing, let's do number 2 first. Okay, so what comes out of number 2 will feed into the meter and then put it back to the circuit. And so I'm getting 16.64 amps coming out of number 2.
Units.
Milliamps, yes. Milliamps. And so if I hook this all back together, we could look at what's coming out of resistor number 3. And here, since I don't know which way it goes, I'm kind of curious. I'll pay attention to which one I am putting out of here and see if I get a positive or a negative. And it looks like I get an 11.64. And I am a little surprised it's so big. But notice it's a positive, and so this would tell me that of this, 16 and a little more is coming down, splitting, and most of it's going this way. So this is really charging this battery. This is sending 11 that way. And so very little of that is going this way. It looks like maybe just about 5 milliamp, well, exactly 5 if I take the subtraction there, is going this way. And so I will feel really safe about my measurements if I get a 5 over here. As I feed things back together, a little higher than 5, but within reason here, I get 5.34 milliamps. And other than a little bit of maybe some connections or, there we go. I like that better. Well, I had it at 5.05. That was really a good one. But why don't I do the 19? And so our contacts are going to make things change a little bit. Plus, our meter's not perfect either. So, not a surprise. But I think this is pretty stable, and I'm hoping that's pretty stable. But that comes to the end of the lab. And now let me just point out that, again, besides all those calculations, you have some discussion questions. And I believe there's 5 of them. And let me just scan through them as I come to the end, because I think most of this, with maybe the exception of number 4, you already know. Like the first one says, Kirchhoffs laws are a statement of conservation of what two quantities? I think you know that. I'll leave that one to you. 2 says, using Kirchhoffs laws, why does the terminal voltage of the cell rather than the EMF matter? Maybe I should expand at that. You might recall that I just hooked this up, and for you to do the calculation, I wanted to know the terminal voltage, not the EMF. And again, I guess I would say, I didn't put it in the picture, but inside the battery is a little resistor. And we want to know the whole voltage, including the EMF and the internal resistance. So I think the best answer here is the terminal voltage includes not only the voltage from the EMF, but also the voltage from the internal resistor. If all I did was the EMF, I would be missing part of it. So that's why for this setup, we wanted to actually hook it up. Then we wanted, because now that it's hooked up, it's actually current is flowing, going through that internal resistor, and we would want to know that. So the terminal voltage was important for our calculations to match our measurements, because in the real world, our measurements are actually including the internal resistance of that second battery. If we only did the EMF and we ignored that second battery's internal resistance, our calculations would be more off than they are already. They're always going to be off a little bit because our measurements and calculations don't exactly match. 3, compared the calculated value of the current in the 750 ohms, so that's what you did in step 6, compared to what I did, or I'll say we did, when we measured it. And so compare the current in the number 4. And that's what they're saying there. And then you just calculate the percent difference. Let me jump to number 5 because I want to say more about number 4. But number 5 says, when you were doing Kirchhoffs laws, it says here, what is the rule for assigning a sign? And what they mean by that is plus or minus. When do you put plus or minus? When you're doing Kirchhoff's loop rule and the voltage changes, when do you put a plus and when do you put a minus for a resistor? If you don't already know, let me say it now. This is what you've been doing, I think, in most of these chapters, well, 27 and 28. When you go around the loop and you go with the current, you put a negative sign for the voltage change. When you go against the current, you put a positive sign. So if I were to go around the loop in this fashion, I would be going with the current and with the current. I'd put a negative here for each of these. But if I were to do a calculation where I'm going the other direction, I would go against the current, so I'd put a positive, and I'd go against the current, so I'd put a positive. And so they just want to remind you that as you're doing Kirchhoffs laws, the voltage change is equal to Ohm's law, that is current times resistance, but then you have to make sure you got the plus and minus right. And that's why when we were in chapter 27, I kept emphasizing that. I think now you're beyond that, but just in case, this is a good refresher question. When is it plus or minus? Now, I say that because maybe the hardest one here is 4, because your author's question 4 is a little different than what you've been exposed to. See, the node rule says this. I'll come back over to here. In step 5, we talked about this. This is how your book presented it, at least the Survey book. I should look at the OpenStax book. It's the way I did it up here. We just like to say the currents going in equal the currents going out. I like that best, but we could do this. We could say pick a node, like node N. So if I come back here to step 4, and I go, okay, pick this node. If it's going into the node, call it a positive. If it's coming out of the node, call it a negative. And then, if you do it that way, you would say the sum of all the currents into a node would equal 0. Because what goes in is positive and what comes out is negative. So you can assign a sign. You can assign a positive and a negative. And so this method is not really what I've been emphasizing. I like this. I just feel this is a little nicer, and it's also what the Survey book does. But the author of your lab manual is referring to this, and I should look at the OpenStax. So to help you with number 4, I'll just give you the answer. It says here, state the rule for assigning the sign to the direction of the current at a branch node. Well, if it goes in, give it a positive. If it comes out, give it a negative. That's the answer to number 4. So that's the one I felt like I better read and help you with. So again, answer those 5. And so again, what you're going to turn in and load up to Canvas are all these calculations, and then also the answer to these 5 questions. And that's the lab this week, and we'll move on to magnetism.